I just want to record that students from third period. All right, so in our packet, could we please just flip over to the back? So we do not have to memorize any of these values or even get familiar with what kind of species do we find the reduction of at the top of the paper, toward the bottom, not at all. You will either be asked to cite the table, the standard reduction potential table, or you will be given values within the problem. For example, just taking a look at this real quick. We're not going to pull from this. You don't have to worry about it today. Like you'll be given values to choose from. So nothing we're memorizing. Remember, these are all reductions and the strength of the reduction. So we can look at these, if they're positive values, as being the intensity of the pull that fluorine has for electrons, or cobalt +3. So the more positive, the stronger. The lower in value, and then we go to negative. Those are not thermodynamically favored. However, the opposite process. So the lithium ion reducing to elemental lithium, that is going to require us to put in, remember, a volt is a joule per coulomb. So to put in that much work per coulomb. But if we would flip it, so if lithium would then oxidize, so if lithium would lose an electron, then it would become a positive 3.05 volts. Okay, you can cite this table whenever you need it. I put this on the back of our packet, but remember, we saw that it's also, there's a more extensive version. So this I got online. It just has a couple more reactions that we may do in class. And then the College Board version here, but also in the back. Okay, to warm up, can we find our way, incredible students, to page 13, page 13. Okay, and so we went over that table because we will need information from that table for question 1. And then just our understanding of terminology for question 2. So can we take about 90 seconds or so and go ahead and answer 1 and 2? Thank you. Page 13. I'm so sorry. Yeah, page 13. more time, start to talk. Start to talk. Okay, excellent. Okay, so we got that single sheet that had terms of this unit in a box. And really, as we're nearing May 2nd, we want to become just reminded and refreshed on terms. So, citing the table, we are looking for the best oxidizing agent. And we just have to know oxidation is loss of electrons. Well, the agent, if it's the oxidizing agent, it is reduced. It is reduced. So I have this reduction table. All of these reactants are gaining electrons. They're all being reduced. So I need to see which has the greatest positive voltage. That's how I know what is the strongest or the best oxidizing agent. So I'm looking for these being reduced. Yeah. So I scan over and I'm trying to find silver neutral elemental. It's not. Okay. Do metals ever reduce? Do metals, neutral elemental, ever become anions? No. Remember, metals can only and will only form cations. Now we could have like a +3 iron become a +2. Okay, that's different. But the neutral never becomes negative. We know that. So that's not even a choice. So then we look, okay, where do we find tin +4? There's tin +2 and tin right there. Now we need to be careful because there could be another tin +4. Here it's just accepting 2 electrons. Could there be another where it's accepting 4? And no, that would be problematic. We wouldn't know which one to choose. So anyway, we just have to be on guard for that. And so the tin +4 is 0.15 volts. And then, my silver, 0.80. And then aluminum +3 is negative 1.66 volts. Or you could just, because it's in order of strongest reducing species or oxidizing agent. So whichever is furthest up on the table. Yeah. So it would be silver ion all day long. Yes, go ahead, Elena. Okay. Okay. A volt is a unit of electrical potential. And 1 volt is a joule per coulomb. But that does not help me to understand what it is. If someone else can explain like per the units. Okay. I think of this, the larger the value, for electrons to flow, there needs to be a push or a pull. Okay. So in essence, it helps me to just think about like a downhill. If electrons are just on a level plane, they're just going to keep doing their thing, be a sea of electrons. But what would cause them to flow to then power something is like a steepness of a hill. Okay, the way we get electrons to flow in one direction, otherwise they're just moving all around, is we have an electrical potential. So I think it makes sense if we talk about like a downhill, and the steeper the downhill, the faster the flow, the stronger the pull, or the more easy the push. If that's okay. So that's what I look at as far as like voltage. That makes sense to my chemical brain. So like the higher the number, yeah. Yes. that really is a yep. Sort of kind of yes. if that's okay, to just say sort of, kind of, yeah. Is that okay? I understand it's a little bit of this, like a little bit elusive, but yeah. Okay, are we good there? So then, what about number 2? Well, it's saying which could not take place at the cathode. And we just need to know, cathode is where reduction happens, yeah? So if we want to know what doesn't happen, well, oxidation does not happen. Oxidation happens at the anode. And cheesy as all cheesy can be, how I remember, it's Val and Val. I shared that, didn't I share that with us on, maybe not, did we get that? I can't remember. Yeah, I can't remember. So oxidation happens at the anode. We talked about the 2 parts of our battery, the 2 half dozen. Okay, very good, very good. All right. So we want to identify what of these is the oxidation. How do we do that? Identify oxidation numbers. So we know neutral, elemental, oxygen, 0. Hydrogen, always +1, except if it's neutral, elemental. And then oxygen, now here is hydrogen peroxide. But even if you called it -2, it's really -1, you'd be all right. Because the oxygen is clearly reducing. So nope, that's going to happen at the cathode. Okay, here, oxygen we know is always -2, except in peroxide. So to be a +2 charge overall, vanadium must be +4 there. And then we have 2 with a +1 overall, so vanadium must be +3 here. Wait, did I do that right? How do you know it is? We don't know. We don't know that it, oh, this is +5. That's why I was wrong. 99.5% of the time, oxygen is -2. I just know for sure H2O2 is hydrogen peroxide. I know that because I work with it a lot. And hydrogen can only and will only be an oxidation number of +1. So therefore, oxygen has to be -1 there. Where every other time, I'm going to say -2. But here it's reduced. Here, -2. See, same thing here, -2. So carbon's +4. And then here we would be -8 +3. Yes, there's another reduction. Let's make sure that this is oxidation. So -2, your nitrogen is +2. -2, your nitrogen is +5. Ah, there's our oxidation. So A. Okay, questions? All right, here's where our fun begins. So let's look at number 3. Given the 2 half reactions and their potentials, which net reaction is spontaneous? Now, Stephen, reduction. Can you have 2 reductions occurring in the same beaker? Why not? Two things can't gain. What's giving? What's giving? So we all can't put money in our pocket unless someone's going to give us money. Yeah, we can want it and we can pull for it, but if then there isn't a source of money. So, and you won't have something lose and then something gains. They go hand in hand. So you'll never have 2 reductions or 2 oxidations. Okay. So it is up to us to decide which one will be the oxidation. Well, pretty easy peasy, because the one that'll be the oxidation will be the one that when we reverse the reaction and change the sign, and then we add them together, it'll overall be positive. Well, if I make this my oxidation, it'll be positive 0.25 volts. But nope, that'll be a negative value. So I know this will be my oxidation. I will have the magnesium forming magnesium +2 and then releasing 2 electrons. That will become a positive 2.37 volts. I'm not asked to find the E of the cell entirely. I just know it's going to be positive, so I don't even have to go from there. If I was asked for it, I would just subtract that and it'd be 2.02 volts. Okay, a positive means thermodynamically favored. So let's see. Now, remember, whenever we are adding what would be our reduction and what would be our oxidation, the give and take of electrons has to be the same. So this takes 2 electrons, 2 moles of electrons, and this gives. If they weren't the same, 2 and 2, I'd have to multiply through by a common factor. Remember all this good stuff, good memories, good memories. So the 2 electrons cancel, and then I just add them together. So I am looking for the reaction that has magnesium solid reacting with the nickel +2 ion to yield nickel solid plus magnesium +2. And that is B, right? Yay. Yep. Okay. Questions? All right. So Ryan came in and said, I learned so much from this robotic competition. Mrs. Gerhardt. Let's go to page 7, please. Okay. No, yeah. Tell you what, false. Let's go to page 9. I was misremembering what Ryan asked. Okay, so Ryan comes in and says, based upon our experience with all these neato robots, can we, Ms. Garrett, make a galvanic cell from this reduction? And I do have this reduction. And I say, well, Ryan, where are the products of this? So we need to go to the standard reduction potential table. Sorry about that I forgot to put the products. Oh, we already know this. Remember the oxidation reduction titration that we did? And our source of iron +2 was FAS. Don't expect us to remember that. But this gorgeous dark purple substance, well, we did something similar to this. And then it created the colorless manganese +2. We created water. Let me get the half reaction. Oh, +2 H2O. There we go. All right. Okay. Well, we have 2 reductions. 2 reductions. So, yes, sir. I shouldn't even do 2H. Right? Oh, this should be 4H+. That's the problem with it. Oh my gosh, Gerhardt. No, that should be 8. And this should, no, you're right. This should be 4. You're right. Thank you. I apologize greatly. Thank you so much for that correction. Oh my gosh, I wrote the wrong one. I looked at my fault. I looked at too quickly. Do you see, look how similar. And then, oh my gosh, no, that's not similar at all, Mrs. Gerhardt. This is the one I should have been looking at too quickly. Aiden, thank you. Okay, to rewrite, I'm going to rewrite it because what a mess did I make? Okay, and then MnO4 minus plus 5 electrons. Holy smokes. All right. We're given both reductions. Okay. Which one, Sophia, do we make our oxidation? We want the most positive value possible. Okay, if we flip this, so here we're adding electrons to the reactants. Here we're adding electrons to the reactant. Both of these are reduction. And we know we can't have two reductions. That won't work. Because if I would reverse this, then I would get a value that's more negative. So this will become my oxidation. All right, so it's going to be iron making iron plus two electrons. And then the E value will be positive 0.44 volts. Okay, that naturally, when they're put into contact, it naturally will go in the direction where it's thermodynamically favored. So it seems like, oh, we're making that the oxidation, but no, it will be the oxidation when all our ingredients are put into contact. Okay, so Ryan's question was, how can we make a battery? Well, I want to show us, if you're asked for the complete description or parts of it, what will we create? Well, these are just the fragments. So this would be, of course, the reduction half cell. And we know the reduction happens at the cathode. And then this will be the oxidation half cell, right? Okay, well, first, we need the balanced equation, So these are balanced, one iron, a positive 2, and then 2 negatives give me neutral and neutral. So they're balanced on sides with number of atoms of each element, but also charges. But are they balanced as far as total give and take? No. So for this reduction, we need 5 electrons, and this can only give 2. So we know the lowest common multiple being 10. So we need to multiply this through by 5 and this through by 2. But remember, voltages do not get multiplied. Voltages are joules per coulomb, not joule per coulomb mole reaction. Just joule per coulomb. They are intensive. They depend on the identity of the substance, not the quantity of them. So the E of the cell, which is something that we'll definitely need, we just add up those E values. Woo, 1.95 volts. That's pretty good, Ryan, great choice. But then for our balanced equation, we would have 2 MnO4 minus. I can't help but go ahead and share phase symbols, although not required of you, plus 16 hydrogen ions, plus 5 Fe yields 2 Mn plus 2, plus 8 waters, plus 5 Fe plus 2. There we go, we're balanced. Okay, so we have our balanced equation and the E of our cell. Okay, next, the drawing. So we know we're gonna have each half cell separated, and we can just go ahead and claim they're gonna be in separate containers or beakers. It does not matter where you put your anode or your cathode. Does not matter. So, Rosie, you choose. You want the anode to be on the left or the right? Sure. And we do need to label which is the anode and which is the cathode. Kyle, what reaction happens at the anode? Perfect. So we go up, to what is our oxidation. And remember, we need all ingredients, reactant and product. And we must have a solid in the aqueous solution for the electrons to be given to and taken from. So in each, we'll have the electrode. And in the anode, we have a solid, your iron. So we have to identify, and you could write Fe or put like a line saying, you know, that's made of iron. Now we know water's here. We know spectator ions are going to be there, but we don't write them. The only other species that we'll have in the anode will be the iron +2. Okay, now we go to the cathode. And that is our reduction. So we go up and we look at all of our reactants and products. And I need my permanganate. You are free to write multiple, but as long as we're identifying one. And gosh, I think that's small. And then we have hydrogen ion and manganese +2. So I'm not trying to jam it in there. I should have drawn it a little bit bigger. I'm so sorry. Oh my goodness. Oh, my poor, very sad. I hate my husband very much. I told you he constructed this. I knew it was just like thrown together, but he admits it. Anyway. Water. Water is known to be there because of the, curvy. So we know water's there. So even though it's a product, we don't have to indicate it. Okay. So what are we missing? Go ahead, sir. Aha. So we must indicate what it's made out of. Whenever there aren't any reactant or product as a solid conductive material, we get to choose. And we're going to choose something that will not react. So to be safe, we choose one of two materials. One is just really inexpensive. And so that's probably the one that we'll have to choose, just being financially responsible. The other, if we have some money, we're going to choose platinum. And so if you do not have a solid as reactant or product, then we choose either platinum. And so we can remember PT for Peter Township, or graphite. Strangely enough, the covalent network solid that is graphite, because the layers are held by Lund dispersion, that enables them to be an electron carrier, strangely enough. They're good enough and really inexpensive and will not react. So, yes. Yes. Yeah. So we wouldn't want to stick our pencil, our wooden pencil. No, because you'll be insulated by the wood. We wouldn't. Oh, anyway. Some things I know. I wish, like, okay, best way to get the graphite out of your pencil, wooden pencil, burn the wood. That took me like a year to figure out. I was trying to like break the pencils and get the graphite out for this, not for any other like illegal thing. For electrodes, I was like, oh my gosh, you know how clumsy I am. And I would just think I was pulling and it would break. And then it dawned on me like, burn the wood. And then the wood all burns and you get just this gorgeous long carbon sample. So anyway, that's how I get it for us.
I remember my sister did like a project on that and she like, I don't know when she did it, but she like, and like, it was just so bad.
Well, usually when I need to do it for us, I'll just burn a bunch of pencils. The Ticonderoga are the best. The best. Holy smokes. Yeah. And I'll set my bunch burner and I'll put like ring stands and just burn the wood off. It's amazing. I'm sorry. So I don't know if our new fume hood can hold it, but the old one, woo, yeah, no worries. Yeah. All right. So what are we missing? Well, we need these to be in contact so that these will push and this will pull. And then we know we are missing salt bridge. So unless the contents are identified, we can just label it as a salt bridge. And you can make it as you-ish as you like. And I'm just going to go ahead and then salt bridge. We need one more thing. Now we understand here is where you would have a voltmeter or have the light bulb or whatever you're trying to power for the movement of electrons. But the other thing we need to show is electron direction. So do the electrons come from the anode or from the cathode? Yep. So electrons in a voltaic cell will always flow from the anode to the cathode. So in a complete drawing, we have the half cells with ingredients, ions, and electrode. We have the anode and cathode labeled. We have the salt bridge and direction of electron flow. Yes, sir. Who can answer that? Go ahead, Elena. Perfect. Do you want to add, Tess?
So it'll eventually stop.
So while these oxidation reduction reactions are happening, this is becoming more and more and more positive. It will naturally stop because nature won't do that. And so we have in the salt bridge, it's maybe filter paper, a paper towel that is just soaked in soluble salt. And as this is becoming more and more positive, cations will flow in. And then as this is becoming more and more negative, more and more positive, anions will flow in as this is becoming more and more negative, cations will flow in. Yeah, sorry. Okay. All right. Well, this would be like the physical drawing, but there's another method that's been created that we have to be able to interpret or create ourselves, and that's called line notation. And I have the line notation on another page, so I'd like to do it for this specific reaction. It makes this example. Okay, so if we were asked for the line notation, so we would only give this if we were asked for it or interpret it. Okay, so the line notation includes lines. Well, all right. In line notation, now the physical setup, it does not matter if we put anode on the left or anode on the right. Does not matter. Okay. But in the line notation, we put anode on the left. I'm going to put the line notation here. So I'm just saying the anode and then the cathode. So if we want to begin with the salt bridge, to represent the salt bridge, we use two vertical lines. Okay. Then everything about the anode on the left, everything about the cathode on the right. And we start with the electrode in the anode and then the ions. And then the ions of the cathode and then the electrode of the cathode. The electrode is the solid. Okay. And if we have multiple items, multiple ions, and they're all aqueous, we distinguish them and separate them with a comma. But if two things like the electrode has to be in the solid state, and then ions, they're not going to be solid, they're going to be aqueous, we would separate them with a vertical line. So going back to this example, the anode is the oxidation. And so we start with the electrode, iron, and then we have the iron +2 ion. That's it. But in that same example, the reduction, doesn't matter like what you want to start with. We chose either platinum or carbon to be the electrode. And as long as they're here, it doesn't matter the order. We have the MnO4 aqueous. We have hydrogen ion aqueous. And we have the manganese +2 aqueous. And we have the choice to include water or not, because we know it's there. Tess, what do you think? Okay, so then the electrode, and I'm gonna go with graphite, just be economical. So if you are given this line notation, the question might be, what species is the electrode for the anode? What is the electrode for the cathode? What is the ion that's undergoing oxidation or something else like that? Okay. Okay. Could we just end? All right. Go back to page 13. Can we answer 4? Stephen? Okay, voltaic, galvanic, and Daniel cell. And we could even see it called thermochemical cell. That just means it is thermodynamically favored. It does work for us. It moves electrons. So that just means negative delta G, E of the cell is positive. There's actually a song. And it's one of those songs that gets stuck in your head forever. It is not so nice. We start at the anode. It's like starts like that. I can't sing what for the life of me. And the electrons move to the cathode. That would help here. D is our answer. All right, enjoy the rest of your Monday. It is so good to have you guys back, and congratulations.